The topic of molecular polarity can be a little bit confusing. Now, first of all, we're only going to talk about covalent molecules. If we have a molecule that is two atoms of the same element, so something like diatomic oxygen. Remember Dalton's atomic theory that all atoms of the same element have the same properties. So each of these oxygen atoms has the same electronegativity value. These bonds between oxygen, therefore, are nonpolar covalent bonds. They do not have a partial positive. They do not have a partial negative. They are nonpolar covalent bonds because those two atoms of oxygen share the electrons equally. Same thing can be said for diatomic hydrogen. This is the Lewis structure for diatomic hydrogen, and each of those atoms shares those electrons equally. That is a nonpolar covalent bond. Now, when you have two different elements bonded together, something like carbon monoxide. So carbon monoxide looks something like this. Then you have an electronegativity difference. That electronegativity difference pushes pulls the electrons towards the oxygen because oxygen is more electronegative than carbon. And I know that because oxygen is closer to fluorine. Remember your periodic table trends for electronegativity. Fluorine is over here. And we increase in electronegativity as we move towards the right and as we move up on a column group or family. So as we move towards the right on a row, we get more electronegative. We go carbon, nitrogen, oxygen being more to the right, oxygen is more electronegative. So what we do is we draw what's called a dipole moment. This is the partial positive side, see the little positive sign, and this is the partial negative sign. So the bonds here are called polar covalent bonds. Now, because this is only a two-atom or a two-element molecule, this is also a linear molecule. Now, with a linear molecule, you can have a polar or a nonpolar linear molecule. And the reason for that is because this two-atom molecule is linear because the definition of the shortest distance between 2 points is a line. Now, when we have a multi-atom molecule, so let's look at carbon dioxide. Carbon dioxide's Lewis structure looks like this. We have our carbon here as the central atom, and then we have our two oxygen atoms. Now, I just said that all atoms of the same element have the same electronegativity. So these two oxygen atoms are equal. And because they're equal, they're going to pull on those electrons equally. So we have a dipole moment pulling this way, and we have a dipole moment pulling this way, equal and opposite. So we have our partial positive on the carbon, and our partial negative is on the oxygen. And this is supposed to be a lowercase delta. I squiggle because I don't have very good handwriting. That's what I do. But that's what that's supposed to be, is a lowercase delta. Now, because these oxygen atoms are equal, and I'm just going to erase the dipoles just for a little bit of clarity, because they are equal and they are pulling equal and opposite in opposite directions of that carbon, and we know that these bond angles are 180 degrees, and this is a linear molecule, this is a non-polar molecule. And it's non-polar because we pull equal and opposite. We're pulling in opposite directions in an equal amount of force. So this is a non-polar molecule. Now, when we get to something like ammonia, ammonia is N with 3 hydrogens. And it has 1 lone pair. Now, this is the only quick and dirty rule for molecular polarity. If you only have 1 lone pair of electrons, it's going to be a polar molecule. You can't be general and say if you have an odd number, because that's not true. If you have one, you will have a polar molecule. And the reason for that is not only do we have these dipole moments all pushing towards nitrogen, they all push towards nitrogen and this electron cloud. So fundamentally, what we have, let's see if I can draw this with a little bit of depth. So if we have this hydrogen coming out towards us, and this hydrogen is a tripod coming to the rear, and we're all pointing up to nitrogen, we're all pointing up to this electron cloud. So overall, the molecule has a dipole moment towards the partial negative of the electron cloud. So that is a polar molecule. Now, another molecule that we use for illustrative purposes is water. Now, water is an oxygen with 2 hydrogens and 2 lone pairs. Now, I'm going to draw these this way. And again, we have our dipole moment. We have our polar covalent bonds because there is an electronegativity difference between oxygen and hydrogen. And the hydrogen takes on the partial positive of that. The partial negative being on oxygen with its lone pair of its 2 lone pairs of electrons. This is a polar molecule as well. When we have something like carbon with 4 hydrogens, it's called methane. And I'm going to draw it this way on purpose. So I'm going to have this hydrogen coming out towards us and this hydrogen receding to the rear. Now we still have those bonds with a partial positive, partial negative. Usually when we look at a carbon-hydrogen bond, we call it nonpolar because the electronegativity difference is very small. Depending on what book you use, depending on where you end up after this class, it's possible that will be called a slightly polar bond. So typically when we have a compound like this, we actually change these H's out. And we change these H's out for something that's a little more clear. So if we put chlorine here, so this is carbon tetrachloride, and I fill in all of those electrons. You see, chlorine is more electronegative than carbon. And because chlorine is more electronegative than carbon, what we'll end up forming is these polar covalent bonds with our partial positive at the carbon. Now, remember Dalton's atomic theory. All atoms of the same element have the same properties. So all of these chlorine atoms have this same electronegativity, and they are pulling equal and opposite because carbon's orbitals have hybridized in order to get as far away from each other as possible. And they arrange around that sphere in order to maximize the distance between them. So we have 109.5 degrees of bond angle. And each of those chlorines are pulling equal and opposite. This ends up being a non-polar molecule because they are each pulling equal and opposite. Now, what happens though if I trade out one of these chlorines for anything? Let's say it's a hydrogen. All of a sudden, we have an unequal sharing. All of a sudden, we have made a polar molecule. It's still a tetrahedral shape, but because this dipole is now pushing towards carbon and the carbon is pushing out towards chlorine, we have formed a partial positive and a partial negative side. Now that's when you have a difference in your terminal atoms. When you have all the same terminal atom, what you can do is you can look at your Vesper chart. We usually just call it Vesper, but your valence shell electron pair repulsion theory chart. If these X's are atoms of the same element, then when you have a linear molecule, you will have a non-polar molecule. When you're trigonal planar, you will also be non-polar. But if you're bent or angular, again, this is only if X is the same element. If you're bent or angular, this is going to be polar. Might be easier if I was writing in a different color. So when you have your equal and opposite, it turns into a nonpolar molecule. So this one would be polar. See the one lone pair? Here's two lone pairs. This is polar. Here's your one lone pair again. Here's one lone pair. He's polar, and he's polar. So he's nonpolar because, again, equal and opposite. This T shape is going to be nonpolar, and I think the way that they have this drawn is deceptive. But what happens with this trigonal bipyramidal is you have a triangle around the waist, and then you have something up high, and you have something down low. Now, these things are going to try to get away from each other. So if I have X's around the waist, then I can have my lone pairs here. That's a nonpolar molecule. Similarly, if I have three lone pairs, then we switch, and these become the lone pairs, and these become my X's. So that is also a nonpolar molecule. Square planar for the same reason, that's nonpolar, again, when all of the X's are the same. This, however, this is going to be a polar molecule, and this is polar because we have the 4 places around the waist now. So we have 4 places in a plane, and we have an up and a down. So if we only have 3 X's and 3 lone pairs, we can't distribute them to make them equal and opposite one another. So that's going to end up a polar molecule. This, however, is going to be nonpolar, and you see it's a linear shape, linear shape, linear shape, they end up nonpolar. So you can start picking out the trends that way if it helps you.